Hello one and all, welcome to another online video by Einstein Academy. In this video, we'll be looking at learning outcome B from the topic of theories of acids and bases from the JCH2 chemistry syllabus. Learning outcome B states that candidates should be able to show understanding of and apply the Brønsted-Lowry theory of acids and bases, including the concept of conjugate acids and conjugate bases. So let's begin. So in the previous lecture, we talked about the Arrhenius definition of acids and bases, whereby Arrhenius acids are substances which dissolve in solution to form H+ ion, while Arrhenius bases are substances which dissolve in solution to form OH- ions. So this led to a problem, and let me discuss what the problem is first. It's just a recap of what we did in the last lecture. When HCl, hydrochloric acid, reacts in solution with aqueous ammonia, you will form a salt and water, and the hydrochloric acid actually dissolves in solution to form a H+ cation, while the aqueous ammonia actually dissolves in solution to form an OH- N ion, and the H+ cation reacts with the OH- N ion to form water. And this reaction in solution is consistent with the Arrhenius definition of acids and bases, since this one dissolves in solution to form H+, and this aqueous ammonia dissolves in solution to form OH-. However, if we were to let gaseous ammonia react with HCl gas, it will similarly react to form NH4Cl solid. However, this is not consistent with the Arrhenius definition of acids and bases, because recall that the Arrhenius definition of acids requires that the substance dissolves in solution to form H+ cation. And since there is no solution anywhere, this reaction is inconsistent with the Arrhenius definition of acids and bases. However, if we were to compare these two reactions, right, let's say we cross out the two waters, right, you can see that essentially it's really the same reaction. It's just HCl reacting with NH3 to give us NH4Cl. And it's very weird if the definition only allows for one reaction to be classified as an acid-base reaction, while the other reaction cannot be classified as an acid-base reaction. So we would like to seek another definition of acids and bases such that it will now allow us to classify both reactions as acid-base reactions. And this is where the Brønsted-Lowry definition of acid-bases come in. So let's look at the definition. In order to improve the robustness of the theory of acids and bases, basically to allow for a broader definition so that we can cover more reactions and say that more reactions are actually acids and bases reaction, Brønsted and Lowry proposed the following definitions for acids and bases in 1923. So they defined acids to be proton donors and bases to be proton acceptors. And note that in this definition, there is no requirement for the acids and bases to be in solution. So let's discuss the difference between the Arrhenius and the Brønsted-Lowry definition of acids. So Arrhenius acids are substances which produce H+ ions in solution, and clearly, if you produce H+ ion in solution, you are also proton donors. So Arrhenius acids are also proton donors, and hence they are also Brønsted-Lowry acids. However, right, as I've mentioned before, Brønsted-Lowry acids do not necessarily have to be in solution. They just have to be proton donors. You can be proton donor in a gaseous state, solid state, whatever state it is in. And hence, Brønsted-Lowry acids do not necessarily have to be in solution and do not necessarily have to be Arrhenius acids. In this context, the Arrhenius definition of acids is actually a subset of the Brønsted-Lowry definition of acids. Comparing the Arrhenius definition of bases versus the Brønsted-Lowry definition of bases, Arrhenius bases are substances which produce OH- ion in solution, and OH- ions are actually proton acceptors, right? Because like OH- ion can actually accept a H+ ion to form water. And therefore, Arrhenius bases are also Brønsted-Lowry bases. But again, there is nothing in the definition of Brønsted-Lowry bases that says that it has to be in solution. So as Brønsted-Lowry bases do not necessarily have to be in solution, Brønsted-Lowry bases are not necessarily Arrhenius bases. And again, the Arrhenius definition of bases is actually a subset of that of the Brønsted-Lowry bases. And if you were to exhibit this, illustrate this in terms of a Venn diagram, basically the Arrhenius definition of acids and bases is a subset of that of the Brønsted-Lowry. Okay, so let's revisit some of the reactions and see whether do they actually, whether the Brønsted-Lowry definition allow us to still classify the previous reactions as acid and base reactions. So if we talk about hydrochloric acid in solution and NaOH in solution, the HCl will act as an acid by donating a H plus cation to NaOH. And obviously then the HCl is a proton donor and will be a Brønsted-Lowry acid. The NaOH will accept a H plus from HCl, and hence it will be a proton acceptor. And NaOH will be consistent with a Brønsted-Lowry base. And hence this reaction is consistent with not only the Arrhenius definition, it's also consistent with the Brønsted-Lowry definition. As it should, because it's a subset, right? The Arrhenius is a subset of the Brønsted-Lowry. The HCl aqueous reacting with aqueous ammonia, you will form NH4Cl. Again, the HCl donates a proton and the NH3 accepts a proton. So this is again consistent with the Brønsted-Lowry definition of acids and bases. And this is an acid-base reaction according to the Brønsted-Lowry definition. However, for this reaction, the HCl gas reacting with the NH3 gas to form NH4Cl, previously this is not an acid-base reaction as covered by the Arrhenius definition because there is no solution involved. There's no solution involved, and actually in actual fact there's no OH minus ions that's involved. However, if we were to use the Brønsted-Lowry definition, the HCl gas will donate a H plus to the NH3, forming NH4 plus cation. This is essentially an ionic compound whereby it's actually NH4 plus, and this came from the acceptance of a proton by the gaseous ammonia from the HCl. So, and this is Cl minus. Okay, so basically this accepted a proton from HCl and HCl donated a proton. So this reaction is now an acid-base reaction if we were to use the Brønsted-Lowry definition of acids and bases. And I hope you can now have an understanding of why we like to use an alternate definition, because this allows us to basically cover a wider range of reactions and say that these reactions are also acid-base reactions. Okay, having covered the Brønsted-Lowry definition of acids and bases, so let me just quickly go back to the learning outcome, right? So I've covered the Brønsted-Lowry theory of acids and bases, and now we would like to discuss the concept of conjugate acids and bases. Okay, so let me move on to that. Okay, so consider the ionization of an acid, Ha, in water. Okay, so as in this is just a schematic representation of an acid. It can be like HCl, HNO3. It doesn't matter what the anion is, right? Because like the key is really the H plus ion. Okay, so if an acid ionizes in water to form H3O plus ion, this will be the reaction. HA reacting in water to form H3O plus and A minus. Now, if this is a strong acid, the reaction will go to completion. We haven't really done in proper we haven't done formally the definition of reversible and irreversible reactions, but I guess you have a brief understanding of it if you came from O level. So irreversible reaction is one that goes to completion because, whereby at the end of the day there are no reactants left, and an irreversible reaction is a reaction whereby at the end of the day there will be some reactants left and there will also be some products left in the entire reaction mixture. It doesn't go to completion. Okay, so for a strong acid, the reaction goes to completion because the definition of a strong acid is that it dissociates completely in water to form H plus ion, so there will be no reactants left. So for a strong acid, because the reaction essentially goes to completion, right, the backward reaction doesn't happen, right? Because if the backward reaction happens, right, then you're going to end up with actually some of the reactants left in the reaction mixture, and that is not what happens in an irreversible reaction. In the forward reaction, HA acts as the acid while this acts as the base. So going back again to the Brønsted-Lowry definition, this donates a proton, this accepts a proton. When this donates a proton, it forms the A minus, right? So this is the acid. When this accepts a proton, it will become the H3O plus. So in this case, this is the base, while this is the acid. However, as I mentioned, for a weak acid, the reaction is reversible and the backward reaction is significant. At the end of the day, there will in fact, a lot of HA remaining, and there will only be small amounts of H3O plus and A minus in the reaction mixture. So the way you can think about it is that, so HA will react with H2O to form H3O plus and A minus, but the H3O plus can also react with the A minus in a backward reaction to form, of course, back your HA and H2O. So both reactions in both directions actually happen. Okay, so if we look at the forward reaction, again, HA is the acid, H2O is the base. If we consider the backward reaction, it's actually still an acid-base reaction, but this is the acid because this will donate a H+, which is accepted by A-. So in the backward reaction, this is actually an acid and this is the base. Okay, so hereby comes the idea of conjugate acids and bases. So this is the acid, and when it reacts, right, it will form this. So it's kind of like these two are a pair. So this is the acid, and this is the conjugate base of this acid. Basically, the conjugate base is formed when the acid loses a H+. Okay, so the way we talk about this is that this is the conjugate base of the HA acid. Basically, like they are a pair whereby this one forms this one. Okay, if we were to consider the H2O and the H3O+, right? The H2O acts as a base in the forward reaction whereby it accepts a H+ from the acid. And when it does so, it will actually form the H3O+ acid. And this will be called the conjugate acid. The H3O+ is the conjugate acid of the H2O base. And these two are a pair. So basically the base, when it reacts, it will form the conjugate acid pair. And when the acid reacts, it will form the conjugate base pair. Okay, so I hope that this is clear. Basically, like it always occurs in a pair. The acid will react to form the conjugate base of itself, and the base will react to form the conjugate acid of itself. Okay, so schematically, this is always true. Okay, so like as I've mentioned, the acid, when it reacts, it will always form the conjugate base of itself. So these two are a pair. And when the base reacts, it will form the conjugate acid of itself. So this two is a pair. Okay, so generally, the stronger the acid, the weaker the conjugate base. So let me explain a bit what this means, right? So if the acid is very strong, what it means is that the reaction will lie on this side, right? The right-hand side of the reaction. Because if the acid is strong, a large amount of the reaction would happen and you will form a lot of the products, right? And basically and for this to be true, right, the backward reaction must not happen to a significant extent, right? Because if the backward reaction happens to a significant extent, right, then this acid will not be strong because you will form significant amount of reactants as well. But the meaning of strong acid means that there is only large amounts of the products. Okay, so if the acid is strong, the backward reaction is very insignificant, and hence the conjugate base must be weak because the backward reaction doesn't happen to a significant extent. And of course, if the acid is weak, right, then the backward reaction happens to a significant extent, driving the reaction towards the reactants, and hence the weaker the acid, the stronger the base. Okay, therefore for the words vice versa. And this is of course also true for the stronger the base, the weaker the conjugate acid, vice versa. So if this is a bit confusing to you guys, like just drop me a comment and like I'll see whether I can find other ways to explain it better. If you all have any questions, just drop it off in the comments section, and I'll be more than happy to clarify any doubts. Okay, so so consider a strong acid like hydrochloric acid, right? So perhaps that these examples will better clarify what I just said. If you have a very strong acid such as hydrochloric acid, when it reacts with water, it will form the H3O+ cation and the Cl- anion, and the backward reaction doesn't happen, right? Because it's a strong acid. So it goes to completion. So the backward reaction doesn't happen. So this must be a very weak conjugate base, right? If it's a strong conjugate base, the backward reaction happens and it will not be a strong acid because it will not go to completion. Okay, so illustration of if you have a strong acid, the conjugate base is relatively weak. Okay, and it will not accept the H+ from H3O+ in the backward reaction. However, if you have a weak base, such as aqueous ammonia, when it accepts a proton from H2O, it will form the conjugate acid and the OH- ion. But for this case, because it's a reversible reaction, so the backward reaction will actually happen to a significant extent, and hence, this will actually be a relatively stronger acid, so that it can react with the OH- to give you some significant proportions of the aqueous ammonia. Okay, so I hope that these are illustrations of the concept that basically like if the acid is stronger, the conjugate base is weaker. But I hope that you understand that these are relative terms. Okay, don't say that this is a weak base, so this conjugate acid is a strong acid. Okay, that's a totally wrong thing which a lot of students get into, and in fact a lot of schools actually teach it wrongly. This is not a strong acid. It's a relatively stronger acid when you compare to something else. Why can't we say that this is a strong acid? If this is a strong acid, it would mean that the backward reaction goes to completion, right? Because the definition for strong acid means that it dissociates completely to form H+, and the reaction will go backward completely. And if that was the case, then you'll only have the reactants and no products. But since this is in a reversible reaction, this must be weak acids, and this is also a weak base. Okay, it's just that when we compare between different stuff, this is a relatively stronger acid. Okay, so that's the concept of conjugate acids and bases. Okay, so now the last thing that I'd like to cover is self-ionization of water. Water is an interesting thing because it can act both as an acid as a base and as a base. So for example, if you got liquid water here, right, this can donate a H+ to another water molecule, and when this one donates a H+ ion, it will actually form the OH- an ion. And when this one accepts a H+, right, so this one is like minus H+, this one is plus H+, it will actually form the H3O+ cation. Right, so in this context, right, this is the base and this is the conjugate acid, and this is the acid and this is the conjugate base. Okay, so this is called self-ionization because it's acting both as an acid and a base to generate both H+ and OH- ions. Okay, so the degree of self-ionization varies with temperature. In general, if you go to a higher temperature, you will actually, let me see, so it will actually form more of the products. Okay, however, at all temperatures, right, because the H3O+ and the OH- comes from dissociation of water, and you always form a 1:1 ratio. So it means that at whatever temperature, you can have different amounts of H+ and OH- ion. However, it must be true that it's always equal amounts of H+ and OH- ion, and that is what it means for water to be known as a neutral liquid. Water, when we say that water is neutral, we do not mean that there is no H+ ion. We also do not mean that there's no OH- ions. There are H+ and OH- ions, which arises from this self-ionization process. However, it is neutral because this ionization process always produces equal amount of the H+ cation as well as the OH- ion. Okay, so these are some calculations that we'll cover later on when we do acid-base equilibria. So at 25 degrees Celsius, the concentration of H+ and OH- is 10 to the power of -7, and the pH is 7, as we very commonly know for the pH of neutral water. Okay, so let me just go back and discuss this a bit better, right? Okay, so yeah, because I'm not very happy with the way I describe it. So let me just make it clearer. What do I mean that the term where I say it's relative stronger or not? Okay, so for example, if we have one acid whereby this dissociates to form H+ and A-, and then we have another acid, right? Let me just call it HA', okay? Basically, like these are two different acids, and the acids only differ by the anion. Okay, so both will dissociate in this manner. So if this was a stronger acid than HA', right? Then it must be true that this is a weaker conjugate base. Okay, it's a weaker conjugate base, but you need to understand that basically when we use the term stronger and weaker, it's always a comparative term. So if this is a stronger acid, what acid is it stronger than? It's actually basically stronger acid than this. Okay, so HA is a stronger acid as compared to this. If that is true, then this must be a weaker conjugate base than this. Okay, because if this is a stronger acid, it will actually dissociate to form more H+ and more A-, and therefore the backward reaction cannot happen to a larger extent as compared to this one. So remember, the way that I'm discussing it is always a comparative term. This is a stronger acid, it will dissociate to form more A-, so the backward reaction must happen to a lower extent. So this is the weaker conjugate base as compared to this one. Okay, but they are in no way like, so if this is the weaker acid than this, right? This is a stronger conjugate base than this one. It is not a strong base, okay? Because like strong base is always reserved for when it ionizes completely in solution to form a base ionizes in solution to form OH minus ions. Okay, but this is not a strong base. It's a stronger base as compared to this. Okay, so please do not be mistaken by using the word strong base. It's not correct. Okay, we'll cover a bit more on this when we talk about acid-base equilibria. Okay, so that's kind of all for the video, the content that I have for this video. So as a recap, we discussed the learning outcome B, whereby we show understanding of and apply the Brønsted-Lowry theory of acids and bases. So I remind you again, the definition for Brønsted-Lowry theory of acids and bases is that acids are proton donors and bases are just proton acceptors, simple as that, with no requirement for any substances to be in the solution phase or aqueous phase. Okay, and then and again, the concept of conjugate acids and bases, okay, as we have discussed. So basically an acid, when it reacts, it will form the conjugate base of itself. And when the base reacts, it will form the conjugate acid of itself. They basically are pairs of each other. Okay, so with that, I hope you are now able to answer this learning outcome. And thank you for tuning in. And if you like this video, just hit the like and subscribe button. And I will see you in the final lecture for this topic, whereby we examine the Lewis theory of acids and bases in the next video. So stay tuned and see you again.